Okay, everybody, welcome to the afternoon session. So I'm very happy to introduce Julian Sonner, who's going to tell us about A Tale of Tales.
Okay, so thank you for inviting me here to give this talk, and thanks to all the organizers for putting together this really very stimulating conference. So the topic of my talk will be holographic non-equilibrium physics, and the name for the title will become clear, I hope, as I go on. Given that this is a fairly short talk, I'll only be able to give you sort of a tour of the highlights of basically the results of two papers that are on the archive. If you have any questions, of course, you're welcome to direct them to me, but also I encourage you to talk to my two collaborators who are both in the audience, Benjamin Withers and Igor Novak, during any of the breaks or the dinner if you want to annoy them. So, great. So let me start by giving you a rather general introduction to why I think we should be thinking about non-equilibrium dynamics in holography. So non-equilibrium holography essentially is, I think, one of the most powerful applications of holography, but it's also one of the most interesting ones. And the reason why it's one of the most interesting ones is twofold. First of all, of course, as everybody knows, holography really is the statement that in anti-de Sitter space, quantum gravity is just the same as quantum field theory. And in the non-equilibrium arena, that allows us to study things like thermalization or just more general aspects of non-equilibrium physics and have confidence that this is related, at least in many cases, to the physics of black hole formation and also then say its evaporation. So this quantum gravity thing is sort of nicely encapsulated in the non-equilibrium dynamics of quantum field theory. And so there is sort of two approaches that you can take. And as maybe some of you know, I have been taking those two approaches in recent years. So one that I'm not going to have time to talk about today, but I encourage you to ask me privately, is that if you study the non-equilibrium physics of, say, some strongly coupled CFT, if you're able to do that, you can actually learn some very non-trivial things about the late-time quantum physics of black holes. So you're really doing quantum gravity. But also, very interestingly, and that's what I'm going to dedicate my 23 remaining minutes to, is that if you look at essentially the gravity in ADS, you can extract, or you should try to extract universal notions of non-equilibrium physics by studying instead a much simplified gravitational problem. Okay, so the moral of this tale, basically a one-slide summary of what our results are. Let us consider, in fact, so in the second approach where we look at ADS physics to learn something about non-equilibrium field theory, let us consider, in a sense, the simplest non-equilibrium setup that we can imagine, which is a non-equilibrium steady state. And in particular, let us consider a stationary flow of a strongly coupled theory. One might be tempted to say a strongly coupled liquid over an obstacle. So this is a schematic representation of what's happening. I will return to this schematic and explain in more detail what's going on. But essentially, you have a codimension 1 obstacle. So you have a flow which starts, let's say, on the left with a specified flow velocity v left. And of course, other thermodynamic quantities will be specified, like the energy density. And this flow will be strongly non-linearly disrupted by this obstacle. It has to flow over this obstacle. And it will result in a different, sort of far away from this obstacle to the right, it will result in a flow which has different parameters. And of course, there's this interesting transition region. And the most interesting to us aspect of this is that we can actually describe the spatial profiles of such a flow in a completely universal manner, very much inspired by the usual things that go on in holography, but with an interesting twist. And so there is some very universal physics, despite the strongly nonlinear and non-universal nature of the flow around the obstacle. And in some circumstances, you can actually show that the spatial features of this non-equilibrium steady state, so I'm going to use this nest quite a lot, are actually determined by this shear viscosity of an entropy density ratio, which great interest is attached to from the point of view of strongly coupled liquids. And so this leads us to expose certain signatures in thermoelectric probes of strongly coupled liquids that are in such steady states. That's the moral of this tale. But in order to give you intuition, which was actually also the intuition that guided us, let me tell you first about some old tales of quenches. And that's actually some results from a paper that was written in collaboration with our chairman today, a while ago. Actually, I have 3 transparencies on this. The previous speaker, in fact, did a great job describing essentially all of the intuition that I want to glean from this. So I thank him, but I will still go over this in some detail to highlight maybe a perspective that would be useful for my talk. So quench means something that is strongly time-dependent. Okay, so the quench in this holographic context is this quench in ADS. For visualization purposes, let us think about a global quench for now, just this transparency. So what one does is one strongly disturbs, as a function of time, the system, either by an initial condition or by the result of an operator deformation. It's actually the latter that I'm going to think about. Now, in holography, this corresponds to essentially the physics of energy injection from the boundary and the physics of what happens in the bulk. So for example, generically, you might think black hole formation. But more importantly, every time we do this, we find that this quench is something very nonlinear, but in holography, it very quickly gives way to linear physics of the quasi-normal modes, these Q and Ms. And, studying it either through the quasi-normal modes or fully nonlinearly, we can track endpoint functions, entanglement entropy, post this quench, and we can extract interesting physical quantities. And okay, this last thing is just a parenthetical remark. Basically, you can study thermalization of closed quantum systems in this way. Now, let me give you an example of such a quench. So this is the holographic superfluid or holographic superconductor. We're sometimes a bit fuzzy about the terminology. So I'm looking at a Poincaré ADS, and I have a system which has an order parameter field which allows us to study the condensation of this order parameter and breaking of symmetry dynamically. The way that we do this is by introducing an approximation to a delta function, Gaussian basically, that sources the order parameter. So we kick in some energy and we also source the order parameter. And of course there is parameters that tell you how quickly, like this timescale tau bar, and how hard you kick it with a delta. What happens is that this initial state, well, for technical reasons, it actually already has a horizon. Okay, so we start not really at 0 temperature. This will be disturbed by this source. There is some nonlinear evolution. Okay, so the horizon will, in response to this, move out. And we will find some late time dynamics of this in terms of just this holographic dictionary. So we find a final state at effective temperature, but the question is, how is this final state at some effective temperature approached? And in this case, what you get is, you get 3 different regimes. You get a regime where basically the final non-zero order parameter is approached with an oscillation. So the order parameter is non-linearly disturbed as a function of time. It undergoes some oscillation, and then it hits the final value that it has at this effective temperature. There is also a mode where it basically decays completely without oscillation to a non-zero final order parameter. And finally, there is a decay where it goes with a pure damped decay to a zero order parameter. Excuse me. This is non-zero. This is zero order parameter. And essentially, you can label it by the final effective temperature of the final state. Now, this is the result of one of these nonlinear time-dependent simulations, but really the moral that I want to extract from this is that all of this can be understood by studying these collective modes, the so-called quasi-normal modes of the system. That was also the case, or well, to a large extent the case in the previous speaker's talk, so this point I think is well made. This is a universal feature in holography. So by studying, instead of the full nonlinear dynamics, just the dynamics at late time in terms of these so-called quasi-normal modes, we find that we can actually characterize those 3 modes just by analytic features of these quasi-normal modes, which are posing correlation functions at real momentum and complex frequency. So for example, the oscillation corresponds to the fact that these 2 modes, we're supposed to forget about this mode here that is at the origin, that these 2 modes actually have a non-zero real part as well as an imaginary part. Whereas the at pure decay corresponds to the fact that this guy has only an imaginary part. Now, in other words, as a function of the input parameters which produce the final equilibrium state, we can get different phase portraits of this system. And given what these quasi-normal modes do, leads us exactly to predict the mode of equilibration. And if these poles somehow exchange dominant as a function of the quench parameter, you find this non-equilibrium phase transition here. And associated with these kind of phase transitions, you can also think about having something like critical phenomena and so on and so forth. Now, the upshot, basically, I want to move on to the steady state, is that despite things being nonlinear, there is something universal, just a property of modes around the final state. And basically, most of the dynamics is captured by these universal modes and their phase portrait. So what I'm going to basically spend the rest of the talk on is I'm going to tell you what kind of modes we should focus on in non-equilibrium steady states and what we can learn from them. Now, this last remark here is simply that because this is so universal, these modes, you can actually find them in various other systems, even in some simplified versions of BCS dynamics by these three authors. Okay. So let me go then to tails of steady states. So this will be tails in a different sense, but you will very quickly realize how they are related to these tails as well. So let me give you just a little bit of history of steady states in holography. So a non-equilibrium steady state is essentially a configuration of the system which is out of equilibrium but still independent of time. So such states can be engineered. They can also be realized in holography. So here I have two examples which essentially focus on studies which were motivated by condensed matter physics, but there are also other examples that exist in the literature. The first example that I'd like to highlight is a current-driven steady state, where basically you apply an electric field and you can apply a very strong electric field. And the sort of quantities that you might want to study are things like nonlinear conductivity, which was studied by these authors, two of which are in the audience. And you can study that very elegantly and analytically, which also allows you to, in fact, find some fluctuation theorems, so go beyond, so the transport actually have higher moments and fluctuations, which is something that I studied a few years ago with Andrew Green. And actually a similar pattern emerges. So this was a current-driven steady state. You can also think about something like a heat-driven steady state. Again, some of the authors are in the audience. And essentially what was done here is you take two reservoirs at two different temperatures, so two CFTs at two different temperatures, you put them together, and you then ask what happens as a function of time. And what happens as a function of time, excitingly, is that actually a steady state region forms in between two emanating shocks. It's a little bit more subtle than that, but one can say it like this. And you can characterize this steady state region using insights from holography. And again, because these insights are very geometrical, you can actually use this to get full out of equilibrium fluctuation relations also in this context. So what I'm going to do now is I'm going to add to these examples of non-equilibrium steady states a third example, but I'm going to focus on the spatial structure of these steady states. So here is what we're going to do. So this is less of a schematic. This is actually what happens sort of spatially. So we have this left equilibrium, which is characterized, let's say, simply by the flow velocity VL. We have a codimension 1 obstacle. This codimension 1 obstacle could be oriented at some angle theta to the incoming flow. But it is most easily modeled. Well, let me just say that this will disturb the flow and it will give us a different right equilibrium. And the way that this right equilibrium is approached could be a pure decay or it could be a symmetry, as is, for example, indicated here. But let's just keep in mind that this is spatial here, right? This direction is spatial. And so the way that you can set this up, the easiest way that you can set it up in holography, for example, is by introducing a source for a component of the boundary metric. And the source for the component of the boundary metric schematically, so J for the metric G, is that along this special direction that we break the translation invariance in, you have essentially the same Gaussian, but now as a function of space that we saw earlier in the quench as a function of time. So this compressible flow is non-linearly disturbed by the obstacle, but we find some universal features. So this is then the perspective essentially relating to what I said in the beginning. This is really a 90-degree version of the time-dependent quench. Okay, this all sounds a bit counterintuitive. I hope to elucidate a little bit more later. But essentially, what we have is we have something that was actually in a previous work called the spatial quench by Paul Figueras and Toby Wiseman. And so you start with the left equilibrium, which is really at infinity, but I have compactified this spatial x direction. You have some spatial evolution that is triggered by the obstacle, and then you have some right equilibrium that is approached. And essentially, in the bulk, this has the result that you have also an interesting shape in the x direction of the horizon. So we turn a standard quench by 90 degrees, and the dual solutions are what are actually called stationary black holes that have a non-killing horizon. So the horizon generator is not a killing direction of this space-time. Okay, so that's a good perspective to keep in mind. In a sense, what used to be time has now become a space direction. So now let me tell you a little bit more what I mean by these tails of the non-equilibrium steady state. So you see now the schematic makes a little bit more sense. This just means there is an obstacle here, and this is the direction in which translation symmetry is broken. So then from this nonlinear region, there will be a spatial decay, and this spatial decay should be characterized by something that is analogous to quasi-normal modes. So for example, take the energy density and expand it around what would be the equilibrium energy density, for example, on the left or on the right, E left, right. But it's a static mode, so it has zero frequency. So we have a purely e to the ikx dependent delta E. Moreover, for regularity, it better be the case that this is something that is at least a damped oscillation, something that at least decays to the infinite x to the right or the infinite x to the left. So what we're looking for is a time-independent mode on a background with a finite velocity, which here has zero frequency, more generally speaking has real frequency, but it has a complex momentum. Okay, so the quasi-normal mode was something which had real momentum and a complex frequency. So that's again the inversion of the relationship between these two. However, you say, these modes are clearly not regular, because depending on the sign of the imaginary part of K, you can have a divergence. In fact, the regularity behavior is such that if the imaginary part of K in our convention is positive, then this mode will be regular to the right, but it will be irregular to the left. Whereas if the imaginary part of K is negative, then it will be regular to the left, and it will be irregular to the right. So neither of these modes is regular everywhere, and so I think that is the reason why typically these modes are discarded. However, of course, here, any divergence in these directions is cut off by the nonlinear region of the obstacle. And therefore, these modes are both relevant to the physics. And so I will now give you a little bit more of a definition of these modes that also makes sense in field theory, and I then will argue to you that actually these modes are realized in these steady states, and they actually capture almost everything you might want to know about them. So one way of packaging this information from a purely field theoretical point of view is that you actually look at simply the usual, so let's say, perturbative evaluation of the expectation value of some operator that you might be interested in phi. And this, in this context, can be written as, well, the usual commutator. So I'm actually thinking that f is some source, and then I'm actually sourcing it with the same operator that I'm probing, just, you know, to not introduce too many quantities here. And basically, you can convince yourself that when you have an obstacle of the kind that I described, then the correlation function that describes the behavior to the right of the obstacle can be written like this, with this theta function in terms of the spatial separation. So that's quite strange, of course, and that's the counterintuitive part that I alluded to, but it mathematically and physically makes sense. This object here that we defined, we decided to call it the decay to the right correlator. We avoided the terminology of retarded and so on because that really has to do with time and also the hyperbolicity of the equations and the causality that follows from that. But it is a correlator that contains only modes that are regular to the right. So this is the object that has these spatial collective mode poles in the upper half complex momentum plane. And just a brief remark that every now and then these modes did come up in the literature. For example, in this paper where absorption lengths in holographic plasmas were studied. But what I want to say is that the sort of upshot of all this is that these SCMs, these spatial collective modes, which describe the spatial structures of these non-equilibrium steady states, are essentially the quasi-normal modes of spatial translation symmetry breaking. The quench broke, of course, time translation symmetry strongly. This is spatial translation symmetry. So, right, I will do this very quickly because I'd like to tell you some evidence that this happens and some computations where it happens. So people often ask, aren't these just quasi-normal modes? Well, that's not really the case. So for example, we can write down the BTZ, 2 plus 1 dimensional black hole, which has the following quasi-normal mode spectrum. What you can actually do is you can do a boost of the analytically continued version of this, where essentially you go to the fluid rest frame. Okay, if you think a little bit about this, it means this boost has to be applied, so you're supposed to plug this frequency and this momentum into this quasi-normal mode, and then solve for the complex momentum that follows from this equation. And what you get is this is actually the exact analytical SCM spectrum of the BTZ black hole. But I had to complexify it, and I had to basically apply a complexified boost. That's where in a relativistic system there is some relation between them. But what it also tells you is that there is no such argument, for example, in a non-relativistic fluid where those are really different phenomena, the SCM and the QNM. Okay, one reason why I went through this is also I wanted to introduce this BTZ SCM spectrum, which I'm going to use in a little bit. Another example where you can compute these directly is hydrodynamics. So we take this ansatz here, and we write down the conservation equations for hydrodynamics, and we find that such modes can exist if and only if these dispersion relations, or these kind of dispersion relations, are true. So what you have is you have the complex momentum k as a function of the background velocity. Okay, and it depends on the various thermodynamic quantities like entropy density, bulk viscosity, shear viscosity, speed of sound, and so on and so forth. Let me just highlight that the transverse channel here actually depends on this ratio eta over s, and that will be something quite interesting later. Of course, you could also do this in the charge case, which is in our paper, but I've left it out for simplicity. So, beyond hydrodynamics, we can also study these, for example, using holography. So we basically give boundary conditions that correspond to these boundary conditions in the decay to the right correlator. This is something analogous to studying, say, the retarded correlator in holography. And you can find dispersion relations that include the hydrodynamic, or this one would be hydrodynamic, this one would be hydrodynamic. But of course, they extend them in the same way that the non-hydro quasi-normal modes extend the hydrodynamics in that case. Now, what is interesting is that due to the motion of these poles and these interesting coalescences, you actually get very interesting hydro to non-hydro phase transitions, just like we saw in the time-dependent case. Okay, so if you have more questions about it, ask me, because I think I want to go ahead and not talk about the specific phase transitions. Because I haven't really told you that these things are relevant to the nonlinear. Maybe you believe me, but here is some convincing evidence, just part of the evidence that we have, from actually constructing the full nonlinear solution, the bulk solution that is dual to these flows. So this is a construction of these non-killing black holes in ADS4. So there's a new class of non-killing black holes that we constructed using the so-called Einstein-de-Turk or generalized harmonic method. And if you look at, for example, the behavior to the right of the obstacle, so this is space in some units, okay, you find that the mode that you would guess from this spectrum, meaning the one imaginary part, fits very well the tail of this nonlinear solution. And this actually happens in each case. So here I just illustrate one where the leading one is something that connects to hydrodynamics. Here it's one that doesn't connect to hydrodynamics. So in all cases, the strongly nonlinear behavior around the obstacle transitions rapidly to fall-offs predicted by this SCM analysis. Now, actually, this can even be done analytically, which was something that surprised us. So one can use this Black-Janus solution, which is a finite temperature defect solution, which is exactly written down by these authors. So there is some strange coordinate system, but essentially there's some left of the obstacle and right of the obstacle region, and there's a bulk region. Now, in the language of what I've been saying so far, you can write down an expectation value of a scalar field in this geometry. T is just a temperature, M is just a jump across the obstacle. You inverse Laplace transform it, and what you find is that this is a superposition of all the spatial collective modes. So you get all the spatial collective mode frequencies of BTZ using the inverse Laplace transform of this solution. But of course, if you were interested only in the dominant behavior, you would just take the one which has n equal to 0 here. So that's a complete analytic demonstration that this is in fact the correct description of this spatial feature. Okay, I'll skip the corollary. I just want to finish by saying that this tells you essentially that there are signatures, for example, of eta over S in those spatial decays. So if we go back to this transverse mode, we saw that eta over S was what essentially governed its decay length. So the idea would be to set up one of these nests in a strongly coupled material and then use the spatial structure essentially to measure eta over S. Of course, this is very closely related to proposals, for example, by Falkovich and Levitov. Also, there was a poster on this Poiseuille flow at this conference, also viscosity somehow giving you spatial profiles. But for fun, you can actually, in our case, you can estimate these decay lengths in, say, some strongly coupled liquid like graphene near charge neutrality. And using parameters recently published in experiments by the Geim group, you get at room temperature, for example, something like 0.7 micron for this, this particular mode, of course, using just hydrodynamics at room temperature for normal incidence. So let me conclude. These are a ubiquitous notion throughout holography that collective phenomena manifest as damp poles in the complex W plane, and now also we argued in the complex K plane. Let me skip the time-dependent case. That's an old tale. The stationary case, essentially, we have an excellent numerical and analytical evidence that they really describe most of the spatial structure. You get new non-equilibrium phase transitions with presumably associated critical phenomena. We have just argued that there's a stationary manifestation of shear viscosity, and we have constructed them nonlinearly. So what might you want to do? Well, one thing, okay, this is a little bit of just a personal opinion. I think it would be very interesting to understand, in particular, quasi-normal modes and these spatial collective modes beyond holography. So is there some microscopic approach, for example, in graphene? Or might you be able to access them using some sort of resurgent approach? That would be really interesting because that would generalize these phase transitions that we have here observed holographically, actually beyond holography. So, all right, I think I'll leave it here because I'm kind of running out of time. Thank you.
Got time for one question.
For black holes near extremality, it is known that as you approach extremality, there is a bifurcation of the quasi-normal mode spectrum. I wonder if you might have seen a similar thing happening for your SCMs.
Well, what we have seen, which was one of the remarks I skipped, is this bifurcation, is that related to the emergence of a branch point? Is this what you're saying? So what we can see here, for example, so you have essentially exponential decay at any finite temperature, but if you take the zero temperature limit, either by doing it somewhat by hand at the spectrum or by taking the inverse Laplace transform of the zero temperature limit of this, you actually find that this becomes an algebraic decay. And this algebraic decay actually corresponds to a branch cut in the complex K plane.
Yeah, that sounds similar. One of the two branches of the QNMs, they pile up and they become a branch cut.
That
So
actually comes up all over the place.
Okay, unfortunately we're going to have to cut that closed. Have questions in the break. So let's thank Julie again for a very nice talk.